Different types of loads acting on modern high-tech structures under operating conditions can cause their undesirable vibrations. This fact generates a need to modify the initial structure in such a way as to either exclude the possibility of its going to a vibration mode or to minimize the possible negative effect of vibrations on its performance characteristics. One of the variants of such modifications is to equip the initial structure with elements made of viscoelastic materials, which is actually a method of passive vibration damping. In this case, it is possible to significantly reduce the amplitude of vibrations in the steady-state modes or to increase the rate of vibration damping in the transient modes. However, this approach has certain limitations associated with allowable thickness of the viscoelastic layer, physical and mechanical characteristics of the material used, as well as possible covering area of the structure surface. In the context of the rapid development of smart technologies, the focus of current researchers' interest has shifted towards a different approach, according to which the structure is equipped with the elements made of piezoelectric materials. In this case, there is possible to organize a passive damping mechanism, the essence which is in connecting piezoelectric element to passive electrical impedance having the form of an electric circuit consisting of resistive, inductive, or capacitive elements connected in a different fashion. The presence of such elements provides additional energy dissipation, increasing thereby the damping properties of structures. Current research is devoted to investigation of efficiency of using different combinations of viscoelastic elements and shunted piezoelectric elements in the context of enhancing the dissipative characteristics of vibrating structures. We believe that the proposed approach allows one to extend the possibility of using the existing techniques for passive control of dissipative properties of structures. The successful application of this technique requires the studying of the influence of the arrangement of the additional elements in relation to a host structure and to each other, on dynamic response of the system. The study was carried out on the basis of the problem on natural vibrations for piecewise homogeneous electro, viscoelastic bodies with passive electric circuits. Let's consider the mathematical statement of the natural vibration problem which is exploited within the frameworks of the current research. A piecewise homogeneous body of volume 5, which is the sum of volumes V1 and V2, is under consideration. Here V1 volume consists of elastic or viscoelastic elements, and V2 volume is occupied by piezoelectric ones. An electric circuit of arbitrary configuration can be connected to the piezoelectric part across electrode surfaces. Here we imply that an electric circuit connected to piezoelectric part is absolutely passive. It means that the circuit contains no power sources, and consists only from ideal resistive, inductive or capacitive elements. Variational equation of motion for the body made of elastic, viscoelastic and piezoelectric elements connected to an electric circuit is formulated basing on relations of linear theory of elasticity and Maxwell's equations in quasi-static approximation. The constitutive relations for elastic parts of piecewise homogeneous body can take the following forms 2 to 3. In general case, viscoelastic behavior of corresponding parts of V1 volume is governed by relations 4. In the case of natural vibrations, under the assumption that the system vibrations occur with slowly varying amplitudes and the initial perturbations do not affect the behavior of the system, the constitutive relations 4 for a viscoelastic material can be written in the form 5. Physical relations for piezoelectric parts take the form 7. Let's now proceed to the description of the term delta from the equation 1. This term takes into account all the internal works of electric field with a potential difference plus minus phi for transferring the arbitrary electric charge on the circuit elements. According to the well-known formulas from electrical engineering, the equations for virtual works on each of circuit's elements can be derived in the manner presented on this slide. The solution to natural vibration problem in the current coupled field formulation is sought in the form 13, where omega is complex natural vibration frequency. Here U is generalized state vector consisting of 3 displacement components and 1 component for electric potential phi. The real part of natural vibration frequency omega is circular frequency of vibrations and the imaginary one is damping index, that characterizes the vibration damping rate. Taking into account the form of solution 13 variational equation for piecewise homogeneous electro, viscoelastic body with connected passive electric circuit takes the form 14. And now we proceed to the investigation itself. The aim of this research is in establishing whether a combination of shunted, piezoelectrics and viscoelastic elements can improve overall damping in a system. For this purpose, first we need to consider efficiency of each damping mechanism separately. Next, we need to estimate a contribution of each damping mechanism into total damping properties of a system, when both of them act simultaneously. Within the frameworks of this research, a cantilever plate made of linearly isotropic material is considered as the object under study. A layer having the same dimensions as the plate was considered as viscoelastic element. Piezoelectric element made of PZT4 piezoceramics. Two options of the most commonly used shunting circuits were taken into consideration. These circuits are resistive or circuit, which is made of only one resistive element, and series resonant or L circuit, which is made of resistive and inductive elements connected in series. The formulas for calculating the values which provides the best damping are presented on the slide. Let us first consider an option of modification of the original structure connected with adding only shunted piezoelectric element. In this case, application of both above-mentioned options of shunting circuits allows damping only one vibration mode. This slide presents values of the first two complex natural frequencies of vibrations and corresponding damping coefficients when the circuit is tuned on damping the first or the second vibration mode. Piezoelectric element was located nearby the clamped edge of the plate, which allows providing the best damping of vibration at the first mode. This location provides damping coefficients Kc equal to 0.0104 and 0.095 in cases of using resistive and resonant circuit correspondingly. Here, with an addition of piezoelectric element, almost doesn't affect the mass properties of a system. Next, consider the second option of modification of the original structure. In this case, the entire surface of the plate is covered with a viscoelastic layer. A part of viscoelastic layer, no additional elements are added to the original structure. Geometrical and mechanical properties of the layer are presented on the slide. Two types of viscoelastic materials is considered in the current research. The first one is described by constant complex dynamic moduli, which do not depend on frequency. The second material was accepted to have complex dynamic moduli, which change depending on frequency according to a quadratic law. The examples of the curves used are presented on the slide. This slide shows a change in dynamic properties of the system under study for the first 8 vibration modes for the case of frequency-independent moduli and the case of quadratically increasing moduli. Here it is seen that not only damping coefficients change when the values of complex moduli change, but also a considerable shift of frequencies is observed. At this slide there are presented analogous results for the case of frequency-independent moduli and the case when complex moduli decrease quadratically along with increase of frequency. Here we also see that not only damping coefficients change when the values of complex moduli change, but also a considerable shift of frequencies is observed. These results correlate with ones related to the case of increasing moduli. Thus we have shown the importance of accurate description of viscoelastic material behavior. This fact requires development of non-standard methods and algorithms for obtaining solution to the problem of natural vibrations. Due to the fact that next we consider only single-mode damping for the further convenience, we accept that complex dynamic moduli are constant in the vicinity of the mode to be damped. The next option to be considered is the plate covered with viscoelastic layer, as for the second case, and has piezoelectric element attached to its surface and located nearby the clamped edge. And in this case, two possible options of mutual arrangement are, piezoelectric element and viscoelastic element are on opposite sides of the plate and piezoelectric element is over viscoelastic layer. Here we consider that piezoelectric element is not connected to any circuit. This slide demonstrates complex natural vibration, frequencies and damping coefficients for the first 8 vibration modes of the plate with viscoelastic layer, when piezoelectric element located over the viscoelastic layer. The carried-out comparison between results obtained for the cases of open circuit and short circuit modes of piezoelectric element operation allowed resuming that the presence of viscoelastic layer smooths the influence of change of boundary conditions set on piezoelectric element on damping of vibrations. The obtained results show that damping coefficients do not depend on operating modes of piezoelectric element. The results obtained for the case when piezoelectric element and viscoelastic layer are on opposite sides of the plate lead us to the analogous conclusion. Thus, we can resume that attaching a piezoelectric element, which is not connected to a shunting circuit, almost doesn't affect the damping coefficient regardless the boundary condition set on piezoelectric element. However, if piezoelectric element is located over a viscoelastic layer, it is possible to obtain higher damping coefficients from 3 up to 30% for different vibration modes. So the next modification of the structure covered with viscoelastic layer and attached piezoelectric element related to a connection of external electric circuit to electrodes of piezoelectric element. The first circuit to be considered is the simplest resistive circuit made of only one resistive element. The two above-mentioned options of mutual arrangement, viscoelastic and piezoelectric elements were also taken into account. Values of resistance, which provide the best damping for the first and the second vibration modes, are calculated according to the formula presented on the slide. This slide presents values of the first two complex natural frequencies of vibrations and corresponding damping coefficients when the circuit is tuned on damping the first or the second vibration mode. These results correspond to the case when piezoelectric element is located over viscoelastic layer. Herewith it should be noted that the location of piezoelectric element in relation to the surface of the plate, in essence coordinates of its center of masses, affects the results. Due to the fact that the current location nearby the clamped edge is optimal for damping the first mode of vibration, and not as optimal for the second mode, we can observe better damping effect at the first mode in case when viscoelastic properties is not taken into account. But the influence of resistive circuit on damping properties of the system exhibits not only at target mode. In case when viscoelastic properties are considered, this influence goes down. If we consider a case when viscoelastic element and resistively shunted piezoelectric element are on opposite sides of the plate, we see the same behavior as in previous case. The difference in damping properties for the modes under consideration exhibits much greater in case when viscoelastic properties are not taken into account. And this difference decrease alongside with increase in viscoelastic properties. Next we add an inductive element into the electric circuit and thus we obtain resonant electric circuit. All the other conditions remain the same. Viscoelastic layer covers all the plate's surface, piezoelectric element is located nearby the clamped edge. The two options of mutual arrangement are also as the same as in previous cases. In case when piezoelectric element is over viscoelastic layer, we qualitatively observe the same behavior as in case of purely resistive circuit. But here the difference is in values of required optimal resistance, which are appeared to be much less than for resistive circuit. As a result, the difference is also observed in resulting damping coefficients. For resonant circuit they are considerably higher than for resistive one. If we consider a case when shunted piezoelectric and viscoelastic layer are on opposite sides of the plate, we also see the same behavior as for the resistive circuit. Values of optimal resistance decreases, but the overall damping in system increases. Now let us resume what we finally derived from the carried out research. On the basis of the problem of natural vibrations for electro, viscoelastic bodies with passive electric circuits, it was demonstrated that equipping an original structure with a viscoelastic layer and shunted piezoelectric element allows controlling damping properties of an electro-viscoelastic system. The performed investigations also allowed us to resume that application of combination of viscoelastic and piezoelectric element indeed leads to increase in dissipative properties of a vibrating system. Thanks for your attention.